it's really a pleasure for me because normally I give these talks to people who are not expecting quantum integrable models. And now I can skip a lot of introductory and go directly to the meat. And especially I will show some formulas. I like formulas also. Not as many as in the last three talks, but quite a few formulas. So this talk is based on some collaboration with Riccardo Conti and Andrea Raimondo, and also ongoing work with Gabriele Degano, who was a student, PhD student in Lisbon, Genia Mukin, and again Andrea Raimondo. Okay, so the plan of the talk is a very short introduction, and then I will explain and disclaim. So if the momentum is large enough, the Deste-de-Vega equation for quantum KdV is well posed. And the last part of the talk is to claim the multi-potentials, if you know what they are. They were introduced by Bajano, Luciano, and Zamologikov, are complete, which is proven up to a technical assumption. Okay, the idea is that here we classify solution of the Deste-de-Vega equation, and here we classify most potentials, and we compute the spectral determinant, and we show that the spectral determinant coincides with the unique solution that we have defined via the Deste-de-Vega equation. Now, short introduction. Well, it is a general fact that many interesting objects in mathematical physics can be expressed via monodromy data or generalized monodromy data of a linear ODE in the complex plane. Okay, so this more or less my definition of mathematical physics is what Riemann used to do. So, and in particular, quantum field theories and related geometrical objects are often in correspondence with equations with irregular singularities. This is, for example, the case of Frobenius manifold and topological quantum field theory, and this is also the case of the ODE correspondence that is the subject of my talk. And this correspondence is somehow mediated by what I call the nonlinear Stokes phenomenon, or wall crossing. Okay, so we have a linear Stokes phenomenon. It's just solution of a linear ODE. And the linear Stokes phenomenon is the fact that the asymptotic is discontinuous. But then when we consider H-bar family of, let's say, connection, linear differential equation, and we consider the monodromy data as a function of H-bar, in the H-bar plane, we see the same phenomenon. But now it is not linear because the monodromy data do not live in Cn, but live in some algebraic variety. Okay, just one remark about names is that there have been a few talks about ODE IQFT correspondence, or speaking about that. But ODM correspondence, ODE IQFT correspondence are just two different names for the same object. And I think we should all agree to use the same name. Okay, now let's go to no, I don't see that with any polemic, just because people outside our community may be confused. But we know they are the same things, but it's better to use the same. So now I will define the Bethe equation for quantum KdV. Okay, I fix alpha. Alpha is a real, positive real. I mean, it's greater than 0, but in most of my talk, in the first part of my talk, I will assume alpha is greater than 1. And then another real, which is the momentum, which should be non-negative. So the Bethe equation are the following equation. So the unknown is a real entire function, Q of E, of order 1 plus alpha over 2 alpha. It means that if I am the regime that alpha is greater than 1, the ordering is less than 1, which is very important. Then this function, all roots are simple, and 0 is not a root. So I will normalize Q0 to be 1. Then the second hypothesis is that almost all roots are real and positive. Okay, and actually, in the rest of the first part of the talk, I will look for solutions such that all roots are real and positive. Then there is this condition on the counting function. This is not the physical counting function, the mathematical one. Okay, so N of E, the counting function, it counts the number of roots less than E. Okay, should satisfy this asymptotic. And finally, these are the beta equations. So if E star is a root, I mean a root is a 0 of Q, then this product is equal to -1. Okay, so this is the equations that I want to solve. And a further hypothesis is that the number of holes are finite. Yeah, I will explain what are holes in next few slides. I mean, I assume every of you know what they are, but still, maybe some of you do not. Okay, so I remember, these are the beta equations for quantum KdV. So where do they appear? They appear in the study of the edge asymptotics of the distribution of beta roots of the XZ chain. Okay, there was a talk by Hermann Boss which was speaking about this limit somehow. I mean, this is a very interesting limit. I don't think it's still, I mean, there are still a few things to be understood. Because this reminds a little bit like the edge asymptotics of random matrices, but it's way more complicated. And at some particular point, you get the same answer, so maybe it's really interesting. Then these are the beta equations satisfy the eigenvalues of the Q plus operator of quantum KdV. These were constructed by Bajano, Luciano, and Zamologico in these 3 series of papers. And the central charge, and so I assume so this model is constructed starting from the Derma module of Virasoro with this central charge and this highest weight. And then finally, the same equation is also satisfied by spectral determinants of some anharmonic oscillators, which I will present later. And this was discovered by Dorian Tateo and again BSZ in the 98. And this fact is what is called the ODE correspondence for quantum KdV. So we have this kind of triangle that we want to understand. So in one box, we have the beta states of quantum KdV. In the other box, there are these anharmonic oscillator with Monce's potentials. And in the third box, we have the solution of the beta equations for quantum KdV. So we would like to have a correspondence here, which is still very unclear. And today, I will concentrate on these 2 boxes and the relation. Okay, because the idea is that, so we don't know why this happens, why we have this relation. I mean, I don't have any idea about that. But we can go from one box to the other passing through the beta equation. If we have a bijection here and a bijection there, then we have also a bijection up there, which is the path I would like to follow. Okay, now, the first problem is how to classify solution of the beta equation for quantum KdV. Now I concentrate on the case where all roots are real and positive. This is a great simplification. And also, again, I'm working in the case alpha is greater than 1. So now one introduced the counting function, the ZE, which is exactly what you have. The logarithm of the left-hand side of the quantum KdV, this object. Okay, and it's a logarithm. We choose the logarithm such that the z of 0 is equal to -2p. Okay, just no. The beta equations reads: if E star is a root, a beta root, then z of E star minus 1/2 belongs to the integer. So these are the beta equations written in terms of this counting function. Now, in order to classify solution, we must add the information on which quantum numbers are occupied or not. Because this is just one arrow. We don't have the other arrow. So it is not true in general that if z of E star minus 1/2 is an integer, then E star is a root. Okay, so the solutions are classified once we add information on which quantum numbers are occupied are roots and which are not, and these are called odds. Okay. Now for each integer, so z is a strictly monotone function. So for each integer, k.
Is it obvious that it's...
It is obvious because the roots are all real and positive.
That is not the reason. You have to prove that.
No, it is, yeah. It is, I mean, it is not that obvious,
for
but...
xz, this function is generally not monotonous, right? Maybe in this limit, yes, but it's...
No, well, in this case it's true.
Yeah, good.
There is an explicit expression. I mean, this function z...
You don't have complex roots, okay.
You don't have complex root. It's just a sum of function of term. An infinite number of term, each of this term is strictly monotone. So there is no problem. Okay, so we define Ek to be the point on the positive axis corresponding to the quantum number k. Okay, so z of Ek is equal to k plus 1. And now we say that k is a root number if q over Ek is equal to 0. Otherwise, it is an whole number. Now we have the root numbers from an increasing sequence that we call k of n. And in terms of this sequence, now the beta equation reads like that. Z of E of kn is equal to kn plus 1/2. When we have that q of E is given by this factor. So this gives a closed system for the roots, Ekn. And the system is depends really on this increasing sequence of root numbers. If you have distinct sequences, then we will have distinct system. And our aim is to classify, to study well-positiveness of this equation. Now, let me go back once. Okay. Now we have this ODE and correspondence that we want to prove, or to study. We don't know is that even though we do not know how to prove it, we know many things on all of these objects. So everything must coincide somehow. So, for example, the Verma module is a graded module. Okay, it's graded by and the dimension of each graded subspace is the number of partitions of n. So here we should be able to classify most potential in terms of an integer and the partition of that integer. And also here at the level of the beta equation, we should be able to classify the solution of beta equation in terms of integer partition. And we are almost there because the root numbers, which are sequences that stabilizes. Okay, k of n is equal to n. If n is large enough. And now it is well known that sequences that stabilizes are classified by integer partition. Like this is kind of like the Maya diagram. So for example, if you take the empty partition of the number 0, which would correspond to the ground state, the occupied number would be 0, 1, 2, 3, etc. If you take 1, there is just one partition, which is 1. And the root number will be minus 1, 1, 2, 3, etc. Okay, so we have already arrived to a point where we expect the solution of the beta equation are classified by partition. And now I come to the ODE conjecture for quantum KDD, which was stated in the form that I'm considered by Luciano and Zamologicos in 2003. So, according to them, we fix an integer n, and we assume that the momentum is large enough. Now, for every partition, lambda, I call lambda a partition of n, the beta equation admits a unique normalized solution, q lambda of E and the depending parametric on the momentum, whose sequence of root numbers coincide with kappa lambda of n. So, given a partition, we can define a sequence of root numbers, and we expect that there exists a unique solution of the beta equation. And then the second part of the conjecture is that any such solution coincides with the spectral determinant of certain anharmonic oscillators, which I will describe later. Now, the first result that I want to show is this theorem with Riccardo Conti. So we fix alpha greater than 1, an integer n, and the partition lambda of n. And our theorem says that if the momentum is sufficiently large, the beta equation admits a unique solution whose sequence of root numbers coincide with k and lambda. Okay, so this is almost what was conjectured by Bajan-Lukian and Zamologicos, because if P is sufficiently large, we cannot estimate right now what is the minimal P, I mean the infimum of this P. And then we computed the asymptotics of the beta roots for P large. Okay, it has this form. So there is a prefact. So if you divide the roots by P to the 2 alpha over 1 plus alpha, then more or less you get a constant term, and then some term which resembles more or less like the harmonic oscillator, plus correction over the P over 2. Okay, this is like a non-uniform asymptotics, because this constant depends on n, on the beta root. But we also have a uniform asymptotics, which is much more complicated to.
Can you remind what is P?
P is the momentum.
Twist.
Huh?
In the beta ansatz, it's called twist.
Okay, in the beta ansatz for X and Z, P is exactly the twist plus the total magnetization. A and B will be some gamma function. It's some factor that I don't want to show. Yeah, P for X and Z is like a twist plus total magnetization.
But isn't it, if it's a twist, I mean, it shouldn't be between 0 and 2 pi or something like this?
If it is a twist, but then it's a twist plus the total magnetization. Total magnetization can be any integer. So eventually it's... But this is if you think in terms of X and Z. If you think in terms of quantum KdV, P is just a real number.
But even in X and Z, the beta ansatz are periodic in the twist, but the roots are not periodic.
Yeah, so the fact is that we have chosen, so it's true, no, that there is some ambiguity in the beta equation because of the choice of P, because that depends on e to the minus 4 pi I P. But then we have taken the logarithm and we have chosen a value of. So it seems as an ambiguity, but it actually is not. Okay, and about early results on this, in the mathematical literature there is very little. There is this paper by Arthur Avila, which after Boros was studying, he didn't know it was beta equation, but he was studying that. But for a very specific value of the momentum and for the empty partition in 2004. and using completely different methods, like dynamical systems. And then there is like, the result is using TBA, again for the empty partition. TBA, the problem is TBA exists just when 2 alpha is an integer, so cannot be applied to general alpha. Now, two remarks. Of course, I mean, Yang and Yang in '66, they showed that this, in the logarithmic form, beta equation can be studied by a variational approach. And I think this is also possible in this case. If you take the Yang-Yang functional, in this case it will be infinity. I mean, you have to renormalize this Yang-Yang functional. It probably works. I yet haven't tried.
They use convexity, and this is not usually given for XXZ. You don't have convexity for the Bose-Gas. They study it is convex.
In this case, it is convex because the roots are real and positive. It is convex. But it is convex, but it does not exist at this moment. I mean, you have to define it. Once you have defined it, it will be convex. And so it will be maybe possible to prove. But it's like the space is infinitely dimensional, so it has its drawback. And also, the range, so the range alpha greater than 1, it is sometimes called the semi-classical range parameter, because alpha is equal to infinity will be classical KDV. So this range of alpha from 0 to 1 seems more complicated. I don't know. I haven't given a look at that other range. So the strategy of the proof is standard. I mean, this I learned from many years of literature, which in great part was written by people in this audience. So you take the logarithmic, the equation logarithmic form, and you transform it into what they call a free boundary nonlinear integral equation. That sometimes it's called D'Este-de-Vega equation. Sometimes it is given other names. I don't know. I don't know exactly which name I have to choose. But D'Este-de-Vega was already chosen. The name chosen by Hermann Bose, so I think it's fine. Then I linearize in the large P limit, and I do perturbation analysis. Okay, so the strategy is very standard because this is the strategy that was followed in the physics literature to extract a result. But then the analysis is completely new because to do this perturbation analysis requires a lot of work. So the proof is quite demanding. It's 50 pages, and for me was quite on me, and Riccardo was very demanding. So what is the D'Este-de-Vega integral equation? So we are given a partition lambda of n, and I call big H the number of holes greater than the lowest root. Okay, now the unknown of the D'Este-de-Vega is a tuple where omega is a positive number, which is the left point of integration of the integral equation. H1, big H are the holes greater than the position of the holes greater than the lowest root. And Z is a function from omega in the interval omega infinity, which is differentiable, strictly monotone, and has these asymptotics. As E goes to infinity.
What was X?
Huh?
What was X?
No, X is Z. No, X is E. It's a mistake, yeah.
X was a typo.
X is a typo. I mean, in the paper I always write X, but here I decided to write E. Okay, it's E goes to infinity. Okay, so this is the D'Este-de-Vega equation. It's actually a system. Now, you see, it's the integral part, which is Z of A is equal to minus 2p plus this convolution against what? Against the ceiling function of Z minus 1 half. And then we have these forcing terms, which depend on the holes. Then the second equation is the equation for the boundary of integration. It says the ceiling of z omega minus 1/2 is equal to minus h. It means that we have chosen omega, the left boundary integration, which is slightly smaller than the lowest root. And then we have the last equation, which is the consistency equation for the odds.
You just read the equation without corrections. I mean, so normally in the right-hand side you have exponent.
No, it is the exact equation. So here is the fact. Normally it is written differently. It is written like with 1 over pi m of log of 1 plus e to the 2 pi I z x plus. This limit is equal to z minus the ceiling of z minus 1/2. Well, whenever z is a strictly increasing real analytic function, this.
So that's what I'm saying. So this is already linearized, so you don't.
No, it is not linearized. This function is very nonlinear. So
this bracket.
this is the ceiling function.
Yeah, I see.
The ceiling function is something like that. Okay. But this is essential. Was essential to us because this makes the analysis possible. I mean, so we don't have to do integration on the complex plane. It's just purely real things.
Are you in the continuum or still on the lattice?
No, it's continuous. It's continuous.
But
But it's continuous, but the roots are separated.
yeah, but why do you have omega? I mean, then shouldn't be all the roots from minus infinity to plus infinity?
So it's like that. So all the roots. I mean, we are in the limit, but you don't have to think of x and z. I mean, it's a particular limit of x and z.
On the side, I mean, there is a distribution of roots, and they just choose the original key and because it's periodic.
So here is the picture. You start from 0, then you have a lot of odds, and then you have the first root. And I choose omega here. Okay. I mean, I could make another choice, but I would have more terms here. Eventually, in the large momentum limit, I will have an infinite number of odds, which I don't want to. Okay. Then the linearization is also interesting because here is the linearized version of the Desti de Vega, and essentially it is the same. I mean, it gives you the same answer as WKB approximation because so how it is solved? Normally it is solved like a Wiener-Hopf equation. So what you get is the inverse Mellin transform of some product of gamma function. It's something very bad. I mean, often in the physics literature, one work with takes theta is the exponential. I mean, take the logarithm of the exponential of these things. And instead of the inverse Mellin transform, it's just the inverse Fourier transform. It's the same. This is the formula. But the formula is quite bad because since we want to do perturbation analysis, we want to know a lot about this function. In particular, we want to know that it's positive, it's differentiable. No, differentiable is easy, but it's monotone. To prove from this formula that the function is monotone is crazy. But then we discover a much more useful formula in terms of WKB integral. So the same inverse Mellin transform of product of gamma function is just the WKB integral for this potential. So this potential is this one which will appear in the ODM correspondence. Okay, so we integrate. So this potential is convex. We integrate between the two real and positive zeros, the square root of the potential. And this, well, Xi is the energy of the potential. And this integral, depending on Xi, gives you the solution of the linearized DDD equation. Now, I don't know how to pass from this formula to the other formula. I know how to prove that both formulas satisfy the same equation, which has a unique solution. But it's pretty remarkable that that you can pass from one integral representation to the other one.
But it's simple, yes.
Huh?
It is simple.
It is?
Simple.
Ah, okay. So,
I don't remember, but I remember that I did it without any problem.
but yes, but once you see this, once you have this formula, you already know that what you are computing is some WKB asymptotics for some differential operator. So from this formula alone, you can guess the ODM correspondence, at least for the ground state. You just choose the potential, this potential, and you will get the correct guess for the ODM correspondence.
So how this tau is related to small z?
Well, small z is a linear combination of tau and the derivative of tau.
Okay.
When the parameters depend on, the linear combination depend on p.
I think the gamma functions you have there are just Taylor coefficients for the square root. So if you write series for the square root, so you will get immediately.
Yeah, possibly. Now, just a quick slide about the analysis. The analysis is pretty complicated. It's very complicated because we have to compute these integrals. These are highly oscillatory integrals, but of functions which are discontinuous. So it's really tricky. You cannot use any theorem. You just have to do a lot of estimates. I mean, integrate in every single domain of continuity. And well, it's quite tricky. So because then we want when we want to, this will give the perturbation. We want to prove that this is small. And in particular, we want to prove that this also that this operator is contracted. Okay, which will give us the uniqueness of solution, existence and uniqueness. But this operator on its face value is not even continuous. So one has to work quite hard. But eventually, we arrive to estimate like this for the function and all their derivatives. Okay, so the norm of this operator goes as 1 over p. That's why in the large p limit, we are sure that.
So what is your functional space? You want to use the Banach fixed point theorem, I guess.
Yeah, the Banach. So these are all weighted L infinity space with some weight which is given by this weight for the function, the derivative, etc.
So then it's a complete metric space.
Yeah. It's the purely functional analytic part is standard. The difficult part is to analyze all these integrals. Okay, so this is like the end of the first part of the presentation. So the second part is about the ODE part of this ODM correspondence. So I start with this family of anharmonic oscillators. So it's pretty simple. The potential is x to the alpha, and then we have an angular momentum. And well, in principle, we should work with L greater than minus 1 alpha. But for simplicity, let me assume that L is greater than 0. Okay, now, also, this is not the best way to present it, but the fastest way. So I consider E to be an eigenvalue. There exists a solution which vanishes both at plus infinity and at 0. If I do that, I will get that the spectrum is discrete, simple, and distributed. And it is given by this asymptotic formula. And from this formula, more or less directly, you can read that you can define the spectral determinant. Actually, you can define a bunch of spectral determinant. But the spectral determinant for this eigenvalue problem is an entire function of order 1 plus alpha over 2 alpha.
So this is out from WKB? Or?
Yeah. And well, the fact that this spectral determinant would correspond to the Q plus operator. Then you can define 1 for Q minus, and then you can define others for the transfer matrices. Transfer methods we correspond to Stokes multipliers, but let me just concentrate on this. Now, in the same paper of BSZ that I was referring before, so these harmonic oscillators were studied by Dorian Tote and Bajan-Luciano Zamologico. And they noticed that this spectral determinant satisfies the Bethe equation for quantum KdV. They noticed that they satisfy the Q, the quantum Wronskian, the TQ relation, they have all this bunch of formal relations. And they soon realized that this spectral determinant should correspond to the ground state, eigenvalue of the Q plus operator of quantum KdV. But then there was a problem. What about all other states? Because quantum KdV is constructed on the Verma module. There are an infinite number of states. And so the idea of BSZ, which is very brilliant and rather classical also, is that in order to get a spectral determinant with the very same property, we can add to the spectral determinant, to the potential, a term like this, minus twice the second logarithm derivative of the polynomial. But the polynomial must be chosen in such a way that all the singularities that you are adding have trivial monodromy. This is a very classical construction of mathematical physics. Darboux was already working on this kind of problem. And so the fact is, if this monic polynomial is such that the additional singularity is monodromy free for every value of the energy, then the spectral determinant will satisfy the Bethe equation for quantum KdV. The same Bethe equation, with the same asymptotics. So the conjecture is that you can get all solution of the Bethe equation for quantum KdV from this kind of potentials. So in particular, we should be able to classify the potential satisfies this trivial monodromy property in terms of partition of unity. I mean, partition of integer, not partition of unity, partition of integer. Now, assuming, so if one assumes that this, which is a generic case, that this polynomial has distinct roots, let's say the polynomial has degree n, yes? The polynomial of degree n has distinct roots, then the trivial monodromy conditions are equivalent to this strange algebraic system. So what we want to prove is that this algebraic system, the number of solutions up to the action of the symmetric group is exactly the number of partitions of n. Now, to show you what is the solution to this classification problem, I go back to Darboux, which is this, he was studying this, which is called, maybe, sometimes it's called in literature, rational extension of the harmonic oscillator. So you consider the harmonic oscillator, and you add some singularities, Fuchsian singularities. And so it is written in this form. What you add is minus twice the second logarithmic derivative, some polynomial of degree n, and you want that the additional singularities have trivial monodromy. Okay, it is by Darboux transformation you can construct all these polynomials. So the fact is that it was proven by Oblomkov that it is really like that. I mean, it is easy to construct solution to this problem by Darboux transformation, but it was proven by Oblomkov in 1999 that actually all solutions to this problem can be written in terms of Darboux transformation, which says that this polynomial U can be written as Wronskian of a bunch of Hermite polynomials. Okay, so the complete classification tells us that you fix a partition, lambda, of n, and the solution of this problem will be given by this form. So there is a complete correspondence between partition of integer parameterized solution to this Darboux problem. And this is the core of our result, because what we did, we computed like a multiple scale limit for the Monster potential in the large momentum multi-scale limit. And we proven that in this multi-scale limit, the Monster potential must converge to a solution of the Darboux problem, to a rational extension of the harmonic oscillator. So we have proven that there must exist, if the momentum is large, L is large, there must exist this asymptotic expansion. Okay? So the ZK, the roots of the BSZ equation, have this asymptotic expansion in terms of the roots of the Wronskian over Hermite polynomial associated to a given partition. Okay, now the difficult part here is to prove that given this asymptotic, there really exists a solution of the BSZ system satisfying this asymptotic. But assuming that this exists, then what we've proven that the spectral determinant corresponding to the solution of the BSZ system with these asymptotics actually coincide with the unique solution of the beta equation for quantum KdV associated to the same partition that we have proven to exist. When the momentum, the quantum KdV momentum is related to the ODE momentum by this relation here. And there is a proportionality factor, which is it is a beta function elevated. Okay. So, and we still have, I mean, the proof is conditional because we were not able to prove in full generality that for every partition we can find a solution of the BSZ system with these asymptotics. The problem is that there are solutions for some Wronskian over Hermite polynomials. 0 is a multiple root, and so everything becomes very complicated in the limit. But I want to show you a last formula that, again, we were not able to prove, but we were able to observe, and it's quite remarkable. So when you want to do perturbation analysis of an algebraic system, of a system, you want to compute the Jacobian at the solution, and then do perturbation. So we want to prove that the Jacobian of the equation in the limit is invertible. So the Jacobian of the equation that you write for the Darboux problem, well, it is this matrix built out of fourth power of roots of Wronskian over Hermite polynomials. And we have found an explicit formula for this, for the spectrum, I mean, for the eigenvalue of the Jacobian, which says that the eigenvalues of this Jacobian matrix are the square of the hook length of the partitions, which is pretty remarkable. I don't know how to prove. There is a proof for the case of the, let's say, trivial partition, which corresponds to a standard Hermite polynomials. And well, if you have any idea about this formula.
So by independent of the v's, I mean, whatever numbers you take for the v's, v sub I, v sub j.
No, v, I, and vj are the roots of the Wronskian over Hermite polynomials associated to that partition.
You have a sum over L, and there's no L there. That
L is I or
Lam.
No, L on the side.
the sum is over L,
One of I is
and I and J are outside.
I different from J. I different from J.
Yeah, but the whole
no,
thing, it's a matrix element. It ends already on I and J.
VI should be VL, no?
Yeah,
Inside the
all
sum.
L should be I.
No, but there is an I out. Don't use I.
These are different eyes. One is the sun.
Yeah, I don't remember. I copied this formula from another presentation.
IJ, yeah, it's
PDE means VL. Yes.
Yeah.
L different from K.
Okay, thank you. Well, whatever is the actual formula, it's pretty remarkable that you have like an expression like that for this, for the eigenvalue of this matrix.
It reminds me actually to the Godin matrix.
It's Godin, but it looks like a Godin.
Well, you know, I don't know, this like this, it is related to Calogero model. So this, when you assume that all roots, I mean, the Vronsky-Novermith polynomial has separate roots, these are complex equilibria of the Calogero, of the classical Calogero model.
Well, lambdas would be what for the lambda would be
There is depend from the partition you can tell whether 0 is a multiple root or not, and from that you can see.
yeah, no, but for Calogero you have an interpretation of lambda.
No, I don't think so. Okay, so I'm coming to the end of this talk. So one, I mean, it's a very vague idea, but the vague idea should be, please correct me if you think differently, because I'm not really an expert on quantum field theory, is that if a quantum field theory is beta integrable, I mean, there is some few operators, and eigenvalues satisfy some kind of beta equations. Then the beta equation, the solution of the beta equation for this quantum field theory should be expressible in terms of spectral determinants of some linear differential operators. So this has been observed and conjectured in many, many cases. It means that the beta roots are in general eigenvalues of a possibly self-adjoint differential operator, which is somehow reminds of the Hilbert-Polyer conjecture. But of course, the beta equations are much more, are very strong. I mean, the distribution of beta roots is much simpler than the distribution of the zero of the Riemann zeta function. And apart from this work on quantum KdV, so a part of this project, I've already started to work on part of this project together with Raimondo and Daniele Valeri, and I'm still working on it. So you can think of quantum KdV as the quantization of classical KdV, which you can think as being associated to SL2 hat. So you can think of generalization of quantum KdV associated to any affine Kac-Moody algebra. And Fagin and Frank, it is the same paper that has been cited a lot. So it was written in 2007 and published in 2011. So sometimes it appears Fagin and Frank in 2007 and sometimes 2011. They say that, okay, the same things as for quantum KdV should work also for generalized quantum KdV. And if you have generalized quantum KdV associated to a Kac-Moody algebra, G hat, then the differential operator you have to study are opens with values in the Lagrange dual of this affine algebra. And with Andrea Raimondo, Daniele Valeri, we have taken the opers that were suggested by Frankel, and we were able to construct solution of the beta equation. We were able to define some kind of spectral determinants and to prove that they satisfy exactly the beta equation that you expect. And this And this creates, I mean, we define, I mean, we prove this kind of relation which are called QQ tilde system, or QQ system, which were already studied, and in particular by Tateo and collaborators. They were conjectured to exist, but we actually proved that they exist. So we actually proved that, starting from these opers, we get solution of the Bethe equation. For example, it is quite easy to find explicit solution of the Bethe equation when you specify parameters of these opers, which correspond, let's say, to the supersymmetric point of x and z. Like, we have explicit solution of the Bethe equation for the G2 algebra, which is quite amusing. You can see in the it's written in terms of some Bessel function. But still, we have been able to just to begin the study of it. So we know that from Langland's dual opers, we can obtain solution of the Bethe equation, but we cannot prove that they are the same solution. And still anything, mathematically speaking, about this ODM correspondence. But it's still, for sure it exists. And it's still the massless case. Okay, I'm still working at the massless case because I prefer to approach a problem at the time. I want to do first the massless case and then move to the massless case. Now, about open question and perspective. Open question and perspective about this, the ODM correspondence was already mentioned several times in this conference. What I want to say is this, the correspondence for quantum KDV, which I've studied recently, is just a tiny piece of an enormous field of research, of which we know a lot, which is still very little, because it's really huge. So there are a lot of questions that we want to answer. So how to guess which ODE, if any, correspond to a given quantum field theory? I don't know. I mean, there are people in the audience that know how to do that, but it's not. I don't know how to do that. Once they are found how to prove them, I mean, some of the methods that I've shown you today can be extended to some models, but not to more models. Well, what I've shown you today is just the beginning of this. And then there is like a fundamental question. So why does this happen? So is there like a general theoretical framework from which we can derive all these ODM correspondence that appear every month and on the archive? And at the same level of speculative question is, why is this nonlinear Stokes phenomenon or wall-crossing phenomenon so important in quantum field theory and related geometrical object? These are questions that, speculative questions that will help also to prove this ODM correspondence. Okay, this is the end of my talk.
Questions? So you showed at some point that these partitions on the ODE side and the partitions in the beta ansatz, you could map to each other.
Yeah.
So what about the CS in the conformative theory? Because we know at a certain level we also use partitions to define the descendants. So is it possible to figure out to which descendant a particular beta ansatz solution corresponds to?
Well, this is actually a question I don't know how to answer.
I can answer. So it's exactly, you have one root, level 1, 2 roots, a partition of 1, length 2, length 3, and so on.
No, but
so the number of
specifically.
The number of states, yes, but the Bethe states. The Bethe states, I don't know, to diagonal. I mean, the Q operators act on this graded module, but I don't know how to diagonalize it.
Yeah, but they have the same eigenvalue. Just delta is the same.
Yeah, but it's
I mean, I like just one thing. If you think in terms of, if you think instead of Fermat module, in terms of the free field representation, in the module of have infinite forms. Okay, the basis is really defined in terms of partitions. Okay, so it looks really in that direction, but I don't know.
No, but you could use the Virasolo generators and it also looks partitions.
Yeah, but the fact is that the Q operator, you have to diagonalize the Q operator.
Yeah.
Well, this side, but maybe asymptote in the large momentum limit, I'm sure that it will be possible to diagonalize them, and you will find explicit some partition. But really, it's just speculative because I've never worked so far on this directly on quantum KDB.
Instead of diagonalizing the Q operator, why can't you just diagonalize a few local IM?
Yeah.
You can just diagonalize some local IM.
Integrals of motion.
No, local integrals of motion, right?
Yeah.
And work out the states explicitly.
Yeah, possibly.
It's very easy. It's like on Mathematica you can.
Yeah, but yes, in Mathematica maybe it's, but then.
And then you can map states to.
Yeah, but like it's like I don't know whether like when you do asymptotic analysis like that, it's difficult to do that in Mathematica. Well, I don't know. Yeah, there are many possible answers, and I don't know any.
Yeah.
But many people in the audience probably know the answer, but I don't.
I think there is some contradiction because you say that on the one hand that Fagan and Frankel explain everything, and then on the other hand that still the ODE CFT correspondence needs explanation. If it is explained to them.
No, they conjecture a lot of things, and they wrote some formula.
Huh?
They wrote some formula. I mean, technically there were some ODEs or SLN written by Dori and Tateo, etc. And they just understood, this is like an opera. They generalized that formula. And then in the paper they do a lot of other things. But it's just, that if you know a bit of finely algebra, you easily recognize from the differential equation that Dori and Tateo used to study that these are affine operas. No. Well, the human beings are full of contradictions.
Let's thank the speaker again.